All right, thank you very much to the organizers for inviting me to give this talk at this truly wonderful conference. I should also say that there are no plans in 2019 to have strings in Sweden. We wanted to save you guys some money. What I want to talk about today is some work that we've been doing over the last couple of years. And in particular, I want to focus on this paper that came out at the end of last year with Till Barhier and Raul Pereira. And let me start by saying the following, that the spectrum, at least we believe, the spectrum of local operators in n equals 4 super Yang mills has been effectively solved in the planar limit. Okay? So this is determined by integrability, and in particular, the asymptotic beta ansatz, and this was basically first started by Staudacher, and it continued over the next couple of years, culminating in this final paper here, such that we have basically the complete asymptotic beta ansatz, and so in principle, we can solve the dimensions of operators. Now, there are complications. These are sometimes called winding effects or finite size effects. But there are a whole bag of tricks now that can handle these things. And Kolya Gromov will tell you more about this last one in these Q functions. But the state of the art right now is the following. So a particularly good, nice operator to look at is the Kenishi operator. So the Kenishi operator is just a trace of the squares of the scalar, trace of phi I squared. The phi i's are the scalar parts of the gauge multiplet in n equals 4. And this operator is primary, so it means it's annihilated by special conformal transformations at the origin. And it's a R symmetry singlet. It's an SO6 singlet. So its two-point function of two Kenishi operators will have this form, which depends on the dimension of this operator, delta k. And delta k can only, in the planar limit, can only depend on the 't Hooft coupling lambda. So this is a graph I took from 2009 from Gromov, Kazakov, and Vieira. I hope it's OK, guys. But anyways, this solid line here shows you what the dimension of this operator would be. Actually, not quite the Kenishi, but a superpartner of the Kenishi, in using the asymptotic beta ansatz. And these dots here are the numerical calculations when you take into account the finite size effects. Okay, so I'll come back to this chart in a minute, but I want to say that besides the spectrum, to really solve the theory, we need to know the three-point correlators. So this is a conformal field theory, so it means that a correlator must have this form, which depends on the separations between the operators in this fashion, and everything is determined up to this constant C123. These alphas here are linear combinations of the dimensions of these operators. And if we're talking about single trace operators, one thing we can say is that in the large n limit, the structure constant should behave like 1 over n. Now, more than a decade ago, a lot of work was done on computing these structure constants in the case of 3 chiral primaries. So a chiral primary is obviously a primary, so it's annihilated by the special conformal transformations. But it's also annihilated by half of the Q's. And these are dual to KK modes in the ADS5 cross S5 type 2b supergravity. And a supergravity calculation showed that C123 at large lambda is the same as the zero coupling result. So it's protected. It stays the same through all values of lambda. Now, non-chiral primaries are not dual to supergravity states, but instead they're dual to massive string states. So one type of operator we can consider are what are known as sometimes called heavy operators. And these are operators that are dual to long classical strings that sort of stretch across the large part of the ADS5 or S5. And there has been a lot of recent work, starting with this paper by Yannick et al., to do semi-classical string calculations for three-point correlators. So some examples are doing the case of doing two heavy operators. So these are operators that are dual to the semi-classical strings, and one light meaning basically a supergravity type state. Or there's also been some work doing 3 heavy, so 3 semi-classical strings, and computing it that way. But the Kenishi operator, the one I want to concentrate on today, is neither semi-classical nor is it light. It's basically dual to a short string state. Okay, and when I say short, I should always have to make a clarification. I do not mean that it's part of a short supermultiplet. It's actually part of a long supermultiplet. When I mean short, I mean short. It's actually short compared to the size of ADS5 cross S5. So a natural question you can ask is, can we compute 3-point correlators where we have at least one Kenishi operator, at least in the case when the tuft coupling lambda is much greater than 1? So here's the general idea. Okay, so since Kenishi is short, it basically doesn't see the curvature of ADS5 cross S5. And so in which case, we're going to use the flat space limit. So this was famously done in the case of the spectrum. So in 1998, a very simple argument would make the following claim. So the string size should be of the order of the square root of the inverse string tension. Okay, and using the dictionary, that tells you it's 1 over lambda to the 1/4. Okay, and if lambda is very large, this is much less than 1. So in units where the radius is 1, this size is much smaller than the radius. So then you can basically just use a flat space closed string spectrum and basically argue that the masses for these states have this form, okay, and if this is large, you can forget about the correction when in the dictionary between m squared and delta squared and basically say that this is approximately delta squared. And so delta basically has this form, 2 times the square root of a non-negative integer times lambda to this power. And for n equals 1, we strongly believe that, that the Kenishi operator has n equals 1. As far as I know, there's no proof. But anyways, here's the evidence that that's the case. So let's go back to this GKV plot. Okay, and you see these little dashed lines here. Okay, these dashed lines are basically a fit to a function. Okay, and they fit to a function, and they saw that the leading term in this function is, well, they got 1.99999, so they stuck their necks out and said it's probably 2. And so you can see that the leading behavior of this is 2 to the lambda to the 1/4. So exactly what the string theory prediction would tell you. So this is an integrability type calculation, but it matches onto the string prediction. So we would like to do a similar thing for 3-point correlators. Okay? Eventually, once integrability can make the steps to do 3-point correlators, we want to give it a goal to shoot for, like these people had a goal to shoot for based on a string theory argument. Okay, so for 3-point correlators, we can look at Witten diagrams. So what we have here is we have 3 operators that sit on the boundary, O1, O2, and O3. And in supergravity, these are dual to supergravity states. And so we have boundary to bulk propagators that propagate into the interior. And we're basically told that what we should do is we should integrate over this intersection point where these propagators meet over the entire region inside this ADS space. Okay, and we should also multiply by some supergravity coupling, G1, 2, 3. Now, if the dimensions of all the operators are much, much greater than 1, then it turns out that this integral actually is highly peaked around an interior region of this ADS space. So our idea would be the following. We're going to actually consider Kenishi operators, but we'll basically treat them as point-like outside this intersection region, okay? Outside this red circle here. And they propagate in, and we'll use ADS scalar propagators to propagate them in from the boundary. And then once we're in this intersection region, we'll all of a sudden remember that we're dealing with strings. Okay, and so we'll use string vertex operators. And since this interaction region is relatively small compared to the size of the space, we will use flat space string vertex operators. But then we have to decide which vertex operators we want to use. All right, so here's that same diagram shown slightly differently. So you can actually do the correlator. You can think of it as a path integral for 3 particles in ADS space. So I have 3 particles situated at the boundaries here, x1, x2, x3. And we do a path integral in this ADS space. Okay, and the geodesics, okay, what the path integral sort of localizes onto are these partial circles inside this space. So these partial circles meet at this point here. And we want to sort of minimize the total action that we get for this particular configuration. Okay, so the point that they meet at, S naught is sort of like a parameter on the string. And the point that they meet at is labeled by x, has coordinates x mu in the spatial directions, and z, which is the direction into the bulk direction, and Poincare coordinates there. The action has this form. And you find that when you look for the saddle point where this thing is peaked, okay, it turns out what all it is just the conservation of the canonical momentum of these particles in this space. Okay? So the sums of these three momenta are 0, and also on these circular geodesics, their squareds are minus the dimension squareds of these operators. Okay, so if I exponentiate this, well, exponentiate minus this, okay, that gives me, plugging in what I find for my z's and my x's, this gives me this part here in blue. So this part here, this is what you expect for a three-point correlator in a conformal field theory. Oops. In a conformal field theory. This part in red is basically taking into account fluctuations about this saddle point here. And then I have this coupling G123. Okay, so these alphas, these are the same alphas I had before. These depend on a linear combination of the dimensions. The sigma is the sum of all the dimensions divided by 2. So if I go back to this then, from this path integral here, basically I can read off what the structure constant is. It is this part here, this part in red, and this part here in blue, and this G123. And that's precisely what I've written down here, this C123 part. Okay, and you can show then that this is the same thing that you would get using this work of Friedman et al. When you do the supergravity calculation where you have where you have these gamma functions. You would get, if you took the dimensions to be large, it basically reduced to this. Okay, so one more thing about this G123 is that this coupling, we also have an S5 that's around here. So we have to take into account what the effect of that is. And so what I'm going to assume is my states are basically going to be harmonic functions on the S5. And so they're labeled by some R charges. And so this part in here, this is an overlap integral for 3 harmonics on the S5. Now the V123, this is what I'm going to get from my string theory calculation. So basically this is going to come from some worldsheet calculation in string theory. And so my structure constant will basically be a product of this ADS5 cross S5 overlap integral. So this is the S5 overlap integral. This is basically the ADS5 overlap integral times this V123. Okay, so here's the strategy. So I've already told you that I'm going to assume that these deltas are much greater than 1. And I'll assume that the states are wave packets with wavelengths that's inversely proportional to the dimension. And they have a spread that's inversely proportional to the square root of the dimension. And so we can basically treat them as plane waves in the intersection region. And so this is an idea that goes back to Joe Polchinski in 1999. And then the momentum that we will use for our vertex operators are basically just the canonical momentum from the ADS5 part plus momentum from the S5 part, which is just related to the R charges. And then what we'll do is the normal sort of 2 pi's and delta functions that you get when you do flat space scattering amplitudes, they'll be replaced with those ADS5 cross S5 overlaps. And we will use level 1 vertex operators for Kanishi, level 0 for chiral primaries. The k squared satisfies this. Since we want the deltas to be much greater than 1, we can set j to be 0 for level 1, but not for level 0. And then the coupling factor basically uses the string result. So I can actually go and look in Joe Polchinski's string theory book, volume 1 or 2. Well, volume 2 refers you back to volume 1. And you can read off this formula right here. Okay, and this is the formula we're going to use. So it's 8 pi over the closed string coupling squared times this worldsheet correlator for the 3 vertex functions, for these 3 vertex operators. And in the dictionary, the closed string coupling comes with this factor is pi to the 3/2 divided by n. Okay, so now how do I still need to tell you a little bit more information about how to choose vertex operators. So what I'm going to do is I'm going to show the n=4 superconformal algebra in a manifest SO2, 4 form. So I'm going to sort of collect all the different generators of the conformal group, conformal algebra, into these SO2, 4 Lorentz type generators. Okay, and then the super generators, basically I'm going to collect half of the super Poincarays, the Q's, and half of the superconformals, the S tildes, and I'm going to combine that into one SO2, 4 spinner. I'll call SQ1. And then I'm going to take the other half of the generators, and I'm going to combine them into the other SO2, 4 spinner, Q2. Okay, and then you can show that they satisfy this algebra, and it clearly has the nice part. R here is the SO6 R symmetry generators. Okay, then what I'm going to do is I'm going to define a linear combination of these Q1s and Q2s. I'll call one Q left and the other Q right. I sort of have to pick a direction in the ADS5 space and the S5 space. And so I'll pick a direction -1 in one and 6 in the other. Okay, and I'll call this Q left. It's linear combination. And I have this one Q right. The only difference is the factor of I and the sign here. And then I'll also define some momentum, which are particular components of these Lorentz-like generators here, and also the R-type generators over here. Okay, so in a particular limit then, say if for a particular limit, you can show then that this Q left, Q right is equal to the Poincare algebra plus some ... But if you assume that you have high momentum states coming in, basically, you can assume that this ... is small, and so you sort of reduce to the super Poincare algebra. Okay, so we want the primary operator, so that means that it's annihilated by the special conformal transformations. And is this 5 showing? No? Is that a 5-minute warning? No? Oh, okay. So this is the special conformal transformations. And so if it's annihilated by the special conformal transformations, it's also annihilated, sorry, this is, yeah, special conformal. It's also annihilated by the super conformal transformations. Okay, and when I go back and look to how I defined Q1 and Q2 and Q left and Q right, you can see that what this does is it enforces a Q left is equal to a plus or minus IQ right. The sign depends on which particular spin component you're looking at. Okay, so the first thing you can realize from this is that you automatically have to have a mixing of Never-Schwarz, and Ramon modes. Because if you act with a Q left on a Never-Schwarz plus right, okay, it turns it into this state here. But if you, Ramon, not right. If you do Q right on Never-Schwarz plus RR, it turns it into this combination here. And if you want to match this combination with this combination, you have to sort of cross-relate this one to this one and this one to this one. So it means that both sets of vertex operators had to be there. Okay, so setting them equal to plus or minus I themselves requires both sets of fields. Then we have to sort of find some way of choosing which particular components we want. And so at the boundary, basically this canonical momentum is pointing straight down into the bulk. But then as it gets into the bulk, it sort of curves around like this. And so what you need to do basically is you have to choose your components such that they're orthogonal to this momentum vector within the ADS5 part of our 10-dimensional space. Okay, and then there's also some SO6 spinor indices that are transverse to that. Okay, but that would be the general idea. So we're going to choose, we have these, in the bulk part, we have these new sets of indices, which are defined by the 4D space that's perpendicular to the momentum vector. Okay, and so those that are alpha prime indices will use a plus I, and those that are alpha dot prime, I'm missing an alpha dot prime here. I'm missing a lot here. That's all wrong. Okay, but anyways, half of them are with an I, half of them with minus I. Okay, so let's do a massless example first. So first thing I'm going to do is consider a twisted version. Okay, so instead of saying half the components have a plus I, the other half have a minus I, I'm going to assume that they all have a plus I. And then once I find such a vertex operator, all I have to do is I have to untwist it. Okay, so basically what I'll do, I'll untwist it by rotating the right-hand side of the part of the state, basically by a 180-degree turn in the two planes that I can, the two orthogonal planes that I have in a 4-dimensional space. So the chiral primaries will be dual to massless vertex operators. So I can go back and read Ferdinand, Martinek, and Schenker. And I think I first heard Emil Martinek talk about this at the first string theory conference I ever went to. The momentum are chosen, as I said before, like this. K squared is equal to 0. And we have two types of vertices. We have Never-Schwarz, and Ramon. Okay, so we have world sheet fermion fields on the world sheet. We have ghost fields as well. Okay, this is choosing the -1 picture. If you're not sure what it is, you can go read it in Joe Polchinski's book. And then we have Ramon vertex operators. And these also have twist fields as well. Okay, and these are in the -1/2 picture based on the charges on the ghosts here. And it turns out the only solution to this Q left is equal to IQ right is not particularly surprising. It's basically where you choose these polarizations to basically be the scalars in these two sectors. So basically, this part here is going to be the dilaton, and this part is going to be the axion. Okay? And so it's a mix of a dilaton and an axion. And this is a descendant of the chiral primary. It's not actually the chiral primary. Okay, so to get the chiral primary, we have to untwist. So untwisting changes the dilaton into a graviton. It changes the axion into a self-dual tensor. And then we can find a normalized vertex. Okay, this is in terms of the Nevis-Schwarz vertex here. This is the Ramon-Ramon vertex here. We plug it into this formula. Okay, we do a little work. Okay, and we find this very simple expression for the amplitude for this particular vertex operators. Then, using the dictionary and the overlap integrals, we find that the C123 has this form, and this agrees with Lee et al., okay, at least for large values of delta. Okay, so this is so it works. So we were happy. Okay, so now we want to go to level 1. This should actually say twisted, not untwisted. Okay, and so the relevant vertex operators can be more or less found in the 1980s literature. I thought I could just open up a paper and find it right there, but you had to still sort of work to get them in the form that we used. And we found this paper by Coe et al. Particularly useful. Okay, so this one has about 1,500 citations. This one has 150. This has about 15. So it basically goes down by a factor of 10. But this was a particularly useful paper. And to show you how long ago it was, I was telling Van Proyen that how useful we found his paper. He says, oh, yes, I remember that paper well. It's the first one we ever teched. And he said, we used to set it running, then go out for coffee while the tech was running. So that's how long that was. So if we set Q left equals to IQ right, it turns out we're going to have two types of Nevis-Schwarz vertices. Okay, and these are sort of ones that are sort of symmetric within the indices, and another set that are anti-symmetric within the indices. Okay, and well, these are you can look them up in the paper. And there's one Ramon-Ramon vertex. Okay, that one doesn't even fit on one line. Okay, so that's this one here. Okay, and you can solve for this equation, and you find that basically it has to be scalars. Yep. Oh, 5 minutes. Okay, good. All right. So the results for 3 Kanishi operators. So we untwist it. Okay, so untwisting is not okay. It actually is a lot of steps in there, but I'll just say untwist. And we end up with this normalized vertex. Okay, so it's a combination of these two Nevis-Schwarz, and this Ramon-Ramon. You compute this world-sheet correlator. Okay, and you have various combinations. Okay, and you have some extremely nasty combinatorics, especially this one, because it turns out you have products of 20 gamma matrices. So it's especially horrific. But you put it on Mathematica, it runs for many, many, many hours, and at the end of the day, you get this answer. Okay, so a very simple answer. So a huge simplification. So G cubed times 3 to the 8th divided by 2 to the 9th. In fact, basically, that's why we think we're right, because we figured it had to be a simple answer. So then you plug that back in to your structure constant, and you find this expression. Okay, and so let me just point out a couple things about this. So first of all, you can see that it has explicit lambda dependence. So unlike chiral primaries, okay, it will depend on lambda. Okay, you also have a suppression for large lambda. Okay, and basically this is because you have this factor of 3/4 here to this supposedly pretty large power, so it can be suppressed. Okay, and this is expected basically for these massive type operators. Okay, so let me just say one more. Am I down to 0 yet? I missed the 2. Oh, okay. So let me do 2 chiral primaries and a Kanishi. So doing the same sort of things, you can find this expression. So my chiral primaries, I'm assuming one has an R charge plus J, another has an R charge minus J, and you basically get an expression like this. And if you look at this term here in the middle, you can basically see that this is going to be singular as J approaches delta over 2. Okay, so this is actually the extremal point. This is where the dimensions of the sum of the dimensions of 2 of the operators equals the dimension of the third. And in terms of our saddle point, what's happening is the saddle point is moving up to the boundary, and we're getting a singularity. So to better analyze that, let's go back to the FMMR result. And in that case, what we have is that if you look at the FMR result, there are these products of gamma functions up here. And in particular, there's this alpha 2, which is the sum of the dimension is d1 plus d3 minus d2 divided by 2. And that's going to 0 in the extremal limit. So you can see that a pole is developing in this plate. I think my thing died. Yeah, died. Oops. Well, that part didn't die. The laser died. Anyways, there's a pole here. Okay, and what the pole is telling you is basically that you're having mixing, okay, with double trace operators. So in the case of 3 chiroprimaries, this doesn't happen. Okay, the pole here is actually canceled by a 0 in this part here. Okay, and you cannot, in the case of chiroprimaries, because of R charge conservation, you can't even go beyond the extremal limit. But in our case, in this case, you can certainly go beyond the extremal limit. So sort of illustrate basically what's this in the diagram. So in here, I've sort of showed the dimensions of a double trace operator in the infinite n limit and the dimension of the Kenishi operator as a function of lambda. So this one is constant. Okay, this one is growing like lambda to the 4th. And what the splitting does is basically what the pole does is it gives you a splitting between these because they end up mixing the operators. Okay, and so you can basically read that off from the residue of that pole. Okay, and if you've ever seen these talk by Leonardo Rastelli, when they're doing bootstrapping for the lightest operator, they do have actually this sort of behavior as they come close to crossing a double trace operator. Okay, so anyways, let me finish up. So there's been a lot of progress on 3-point correlators, at least at low loop orders using integrability, and here's a long list of contributors to this subject. And so our hope is that our results will give them sort of a target to shoot for. I should also say that we can do 3-point correlators that contain an operator with a non-zero spin, and this compares favorably with some recent results by this Portuguese group. There are many possible generalizations, okay, more massive operators at n equals 2 or higher, but don't ask me to find the vertex operators for that. You can study 4-point correlators and look at sort of duality from a string theory perspective as far as crossing symmetry is concerned. The simplification suggests that there's some underlying symmetry playing an important role. That's not surprising. And perhaps these results can lead us to the exact vertex operators in ADS5 cross S5. So thank you very much.
We can take a few questions. Yes. Raise your hand, please.
Oh, Nathan. Yes. Well, okay, but it was again taking this limit that we sort of made this identification. Well, in the J, okay, so in that case, the J is basically the J's are actually not coming from the vertex operators per se. They're coming from the momentum part. So we don't have like d to the x to the j power type vertex operators. So is that answering your question, or? So these are well, okay.
Igor.
Thanks for a very impressive talk, a great calculation. Can you explain this? So this suppression 3/4 to the power of lambda to the 1/4, where does it come from? Just from very massive propagators, bulk to the boundary?
I can give you an explanation. So I got the explanation from Thiel, who got it from Juan. So basically, if you go back to this diagram, yeah, here. So in a sense, what it is that one of these propagators, okay, if I just had a 2-point function, say between x1 and x3, say, it would just want to take a different semicircular path. Okay, but basically by putting this other guy in, you're sort of deforming it away from the path it would want to take on its own.
And that costs you a lot of action.
That costs you action, yeah.
Thank you.
Any more questions? On the balcony? Anybody? Okay, if not, let's thank Joe again.